Welcome to The Explainer. Today, we're unpacking a really fascinating new perspective on one of the absolute greatest medical mysteries of our time, Alzheimer's disease. For decades, we've basically looked at Alzheimer's as a physical accumulation of debris in the brain. But what if we've been missing a massive piece of the puzzle? What if the brain isn't just a container for neurons, but a highly coordinated symphony orchestra? And what if Alzheimer's isn't just about the physical instruments breaking down, but about the musicians actually losing their timing? Let's explore a groundbreaking framework that challenges pretty much everything we thought we knew about cognitive decline.
Okay, let's dive right into this, because honestly, this represents one of the most persistent, head-scratching paradoxes in Alzheimer's research. For years, we've known about the physical hallmarks of the disease, right? The amyloid beta plaques and tau tangles. But autopsy and imaging studies have repeatedly shown us something incredibly strange. You can literally have two individuals with the exact same substantial burden of amyloid plaques and tau tangles in their brains, yet one person maintains perfectly normal cognition while the other develops severe dementia. If those physical proteins are the direct, immediate cause of cognitive decline, why on earth do they produce such dramatically different outcomes? It's wild. Clearly, pathology alone just cannot fully explain dementia.
So, that brings us to Section 1, the Alzheimer's paradox.
This disconnect between the physical markers of the disease and the actual clinical symptoms is the entire foundation of our investigation today. To solve this mystery, researchers are turning to what's called the ECEPJ V2.0 Framework. It's a systems-level approach that proposes a really radical idea. The physical buildup of proteins isn't the whole story. The absolute critical determinant of your cognitive health might actually be the preservation of your brain's temporal integration architecture. Put simply, it's all about timing. To really grasp this, we have to draw a sharp line between two concepts. On the left, we have pathology. That's the physical manifestation of the disease, those plaques and tangles. Think of pathology as a really loud, disruptive audience filtering into our symphony concert hall. Now, on the right, we have pathogenesis. These are the actual mechanisms that produce the clinical symptoms. Pathogenesis isn't just the audience arriving. It's the specific moment that disruptive audience actually causes the musicians to lose their rhythm and stop playing together. The physical plaques are there, yes, but dementia only really emerges when they disrupt the temporal coordination of the brain.
Moving right along to Section 2, the brain's timing architecture.
To understand how that rhythm gets lost in the first place, we need to understand how the brain actually keeps time. See, the brain functions as a massively distributed system. For you to form a memory, solve a math problem, or even just recognize a friend's face, information has to be coordinated across multiple spatial and temporal scales. Effective cognition demands incredibly precise signal timing, stable phase relationships, and cross-network synchronization. The ECEPJ framework actually gives a specific name to the successful execution of this timing. They're called NeuroBytes. Now, I know that sounds highly technical, but you can think of NeuroBytes simply as those beautiful, fleeting moments of perfect musical harmony across the brain's orchestra. They are transient periods, just these brief, sustained windows where distributed neural activity synchronizes just long enough to successfully integrate information. Every single clear thought you have relies entirely on the successful formation of these NeuroBytes.
Let's move to this next visual and see how this builds, because here is the exact biological domino effect that creates healthy cognition. It starts at the base level with graded neural codes, which must be perfectly timed through temporal coordination. When that timing is just right, boom, it leads to neurobyte formation. Those neurobytes then allow for large-scale network integration, and the final result at the very end of that chain, healthy cognition. It's an incredibly delicate, highly synchronized biological assembly line.
Which brings us to Section 3, the symphony interrupted.
So, what happens when amyloid beta and tau crash the party? Well, the framework asks us to view these proteins differently, not as immediate brain killers, but as biological stressors. They impose physiological stress on the brain's communication systems, seriously challenging the network's ability to keep its rhythm. Look at the specific physiological stresses caused by these proteins. They alter membrane properties, disrupt axonal transport, and elevate metabolic demand. But most importantly for our symphony metaphor, they increase conduction variability and drastically reduce synchronization efficiency. It is exactly like that disruptive audience throwing off the musician's concentration. They increase the network's impedance, making it harder and harder for the brain to maintain that precise temporal coordination required to form a neurobyte.
And here is how that disruption actually cascades into disease. The sheer presence of amyloid and tau creates network stress. That stress leads to timing scaffold disruption, meaning the underlying rhythm starts getting shaky. Because the rhythm is shaky, we see neurobyte fragmentation, Those beautiful windows of perfect harmony literally start to shatter. And without NeuroBytes, we get large-scale integration failure. That, ultimately, is what results in cognitive decline. So the decline isn't a direct jump from plaques to dementia. It's a cascading, progressive failure of the brain's timing systems.
Let's look at Section 4, the glial support system. Now, what's really interesting about this slide is that if the brain is an orchestra, the neurons are the musicians, right? But they absolutely do not work alone. Emerging systems neuroscience shows us that cognition depends heavily on coordinated timing distributed across both neuronal and non-neuronal systems. Enter the glial cells. You can think of them as the vital stage crew, the acoustic engineers and the subconductors who work behind the scenes to keep the musicians in perfect rhythm. Here we see the crucial labor divided between two massive players in this framework. On one side, astrocytes provide the metabolic support, regulating energy stability and the whole oscillatory environment. On the other side, oligodendrocytes and their progenitor cells, OPCs, maintain the myelin. But get this, they don't just insulate the wiring, they actively regulate conduction timing, synchronization precision, and adaptive signal propagation. Together, this vital stage crew sustains the actual timing scaffold required for those critical NeuroBytes to form.
And this brings us right back to our opening paradox. Why do some people with severe pathology stay perfectly sharp? Well, because they possess highly resilient timing architectures. They have super efficient astrocytic metabolic support and beautifully preserved myelin integrity. Basically, their stage crew is so incredibly effective that they can compensate for the disturbances caused by the plaques and tangles. They maintain their symphony's rhythm, generating NeuroBytes perfectly, despite having a massive, disruptive audience in the room.
Now for the harder part. Section 5, when synchronization collapses.
Unfortunately, these compensatory mechanisms just cannot hold out indefinitely. When the glial support systems finally fail and the network can no longer adapt to the physiological stress of the pathology, we reach a tragic tipping point. This is when the disease truly takes hold, transitioning from a state of manageable biological stress into overt clinical dementia. When that collapse happens, we see the very specific features listed here. We get increased timing variability and reduced phase stability. The NeuroBytes themselves shorten and fragment, leading to network decoupling. In this model, cognitive decline is definitively a systems-level synchronization failure. It is the total, devastating collapse of the orchestra. The critical event causing dementia is not simply the appearance of plaques or tangles. It's the definitive inability of the neurosystems to maintain coherent temporal integration.
Which leads us to Section 6, measuring the missing dimension.
So, the crucial point is, if timing is the key, how do we actually track it? Historically, we've relied heavily on imaging physical proteins, but to truly understand the pathogenesis of Alzheimer's under this new framework, future researchers are planning to quantify the functional network integrity using advanced tools like EEG, MEG, and myelin imaging. Moving forward, we need totally new metrics to look at the timing architecture itself. And this framework proposes these three candidate indices. First, the NeuroByte Integration Index, or III, to measure the stability and quality of integration. Second, the NeuroByte Fragmentation Index, or NFI, to measure integration breakdown. And third, the Timing Instability Index, or TII, to measure scaffold instability, things like phase variance and jitter. The bold prediction here is that cognitive decline will actually correlate much more strongly with these timing indices than with the physical pathological burden alone.
Let's ground just one of those abstract metrics, the NeuroByte Fragmentation Index, in plain English. Essentially, the NFI is a direct measurement of how badly the integration and rhythm are breaking down across the brain. By tracking regional fragmentation and coordination loss, it tells us exactly how disjointed our neural orchestra has become. The hope, and it's a big one, is that tracking NeuroByte disruption could warn us of an impending synchronization collapse long before overt clinical decline becomes obvious to the naked eye.
And this brilliantly illustrates the massive paradigm shift we are looking at today. We are moving away from viewing Alzheimer's as a purely physical, structural problem, just a buildup of cellular trash, to really understanding it as a dynamic, systems-level timing problem. The pathology matters for sure, but the preservation of the temporal architecture, supported by those vital unsung heroes of the glial network, is what ultimately determines whether a mind remains intact or fades away.
Which leaves us with this final, incredibly provocative thought. If dementia is fundamentally a failure of synchronization, a tragic loss of the brain's internal rhythm, could future therapies focus less on just clearing out the plaques and more on reinforcing the stage crew?
Could we one day treat cognitive decline by actually repairing the timing scaffold itself? It's an absolutely fascinating frontier in systems neuroscience, and one that gives us an entirely new lens through which to view the resilient brain. Thank you so much for joining me on this explainer, and remember to keep questioning what you know.